All right, let's look at section 11.2, derivatives of exponentials and logarithms. So we'll be studying the logarithms today. And we're going to start off with some group work. I'll tell you what, let's just go ahead and do this one together. So you have this function, f of x is equal to e to the x minus 1 over x. Let's complete the table of values and determine what the limit as x goes to 0 of e to the x minus 1 over x is. So if you were to plug these into the calculator, you would get the following values. 0.95163, 0.99502, 0.9995. On the other side, 1.0005, 1.005, and then 1.0517. So the limit as x goes to 0 of e to the x minus 1 over x. What is your conclusion? So what are these numbers headed toward? Headed toward 1. All right. So that limit is, in fact, 1. All right, let's calculate the derivative of e to the x. And we'll do it the long way here, right? So f of x is equal to e to the x. So the way to derive a derivative is to use the difference quotient. So the derivative of a function is the limit as h goes to 0 of f of x plus h minus f of x over h. So this is the limit as h goes to 0. Now the function is e to the x, and the first part of this is, of course, to evaluate where the x is x plus h. The x is the exponent, so that means x plus h goes in the exponent. Minus f of x is e to the x over h. All right, next step. We have e to the x plus h. I'm going to split them apart. Okay? Now, algebra would suggest that these have been put together. And remember, you end up adding exponents when it was base exponent, base exponent. So these split apart as e to the x times e to the h. So go back and verify that if I go backwards and I start with e to the x times e to the h, then that ends up with e to the x plus h. Does that check out? If you go e to the x times e to the h, you end up adding the exponents going backwards. All right. Next step. Factor out e to the x. So there's an e to the x in the first term, and then that leaves e to the h. There's e to the x in the second term, and that leaves a 1 over h. remember that this limit is based on the h. It is not based on x. So anything with an x can come out to the front, because technically it's considered a constant for what we're doing here with the limit. The limit is about h's, not x's. So the e to the x can come out to the front. So this is e to the x times the limit as h goes to 0 of e to the h minus 1 over h. And then, lastly, the limit from above with the table. What was the limit as h goes to 0 of e to the h minus 1 over h? That was 1. Yeah. And so this is e to the x. So this is fantastic stuff right here. What that tells us is that the derivative of e to the x is e to the x. It's the same one. It doesn't change. Now, notice that this is different from the power rule. The power rule is when the variable is in the baseline and then you have some power. The thing in the baseline here is a number, it's e, and you're raising it to a variable with the x there. Alright, so what's the derivative of e to the x? E to the x. That's it. That's where it is. Let's do some examples. Example number 2. F of x is equal to 4 e to the x plus 5x cubed. What is the derivative? So the derivative here would be, so we have 4 e to the x. So all these other rules that we know apply, like the constant multiple rule and the adding rule and things like that. So the 4 stays around, and then you take the derivative of e to the x. What's the derivative of e to the x? E to the x. So this is e to the x plus, now the second part is 5x cubed. So that's the normal power rule. So we bring the 3 down, and we get 15x squared. So that is the derivative. So you need to keep all these rules straight. Okay. I see some people do this sometimes. When they try to take the derivative of e to the x, they try to use the power rule and do something like this. This is not correct. That's no good. Because the power here is not a number. The e is the number, and the e is in the baseline. So it's a completely different rule than the power rule. All right. So here are the other basic derivatives for exponentials and logs. The derivative of e to the x is e to the x. The derivative of b to the x, so b is just any number that we want. It could be a 2, it could be a 12, it could be a 46, doesn't matter. The derivative of that is b to the x times the natural log of that base, b. Okay. And we'll see some examples. This next one, the derivative of the natural log function is 1 over x. And the derivative of the log in any base of x is 1 over x times the natural log of the base. Where I see students mess up on this formula is they'll put 1 over b times the natural log of x. It's the natural log of the base, not the natural log of the x. Okay. Now notice that these on the top row, these are very specific. These are for the e. This is e to the x, and of course natural log is log in base e. The rules below always work with these special cases that can be verified. So for example, let's say that I wanted to do the derivative of e to the x, but instead of using the e to the x rule, I use the very general base rule. Then the very general base rule says that the derivative is the base raised to the x times the natural log of that base, where the base is e. Well, what is the natural log of e? That's 1. So this is e to the x. And so this checks out. This works. And you can do the same calculation on the right side. But you got to remember that the natural log of e is equal to 1. All right. Let's do a couple of these here. What is the derivative of 3 ln x plus 3 e to the x? So first we have a 3. What is the derivative of the natural log function? 1 over x. So this is going to be 3 times 1 over x, and I usually just write that as 3 over x. Plus, what is the derivative of 3 e to the x? That's just 3 e to the x. That was the same. Part B, we have f of x is equal to 4 to the x plus x to the 4th. What is the derivative of 4 to the x? Using one of these rules here. So the base is 4 raised to the x times the natural log of 4 plus, what is the derivative of x to the 4th? 4x cubed. Yeah. So hopefully you're seeing the differences in the functions and the differences in the methods that you have to use to find their derivatives. Suppose we have f is equal to the log in base 3 of x, then the derivative would be 1 over x times the natural log of 3, because 3 is the base. And f of x is equal to e to the x minus 2 to the x plus the natural log of x. So the derivative of e to the x is e to the x. The derivative of 2 to the x is 2x. 2 to the x times the natural log of 2. And the derivative of ln of x? 1 over x. There you go. Okay. Example 4. Find the equation of the line tangent to f of x equal e to the x at x equals 0. So to find the tangent line, the equation of the tangent line, we need two things. We need the slope and we need the point. Where does the slope come from? The derivative. And so this is going to be the derivative at 0, f prime of 0. And the point, where does it come from? It's going to be 0, comma, f of 0. Because we're dealing with x equals 0 right here. Alright, so to solve this, let's take the derivative. What's the derivative of e to the x? E to the x. And so then f prime of 0 is e to the 0. What's the value of e to the 0? 1. And then to find the point, we need to evaluate f of 0. That's also e to the 0, which is 1. So the point is actually 0, comma 1. And now we'll find the equation of the tangent line. So y equals mx plus b. The m is the slope, which is right here. So that's 1x, so I'm just going to write x. And the b is also 1. How do I know that the b is 1 in this case? Zero, 1. The B represents what? Y what? The y-intercept. The y-intercept is the point where x is equal to 0. So the point where x is equal to 0 is this point right here, which makes that y value the y-intercept. Right? Think about graphing it. It would be this. You would graph the point 0, 1, which is right there. Well, that's the y-intercept. That's the b. So b is equal to 1. And it'll be 1 like that. All right. Let's look at example 5. Example 5 says, find dy dx if y is equal to the natural log of 3x. Now, again, this is one of those things, we don't know all the rules yet, so we have to do some algebra first. You don't know how to take the derivative of natural log when it's anything other than just x in the argument. So we'll do some algebra. Recall that you can split up logs that are multiplied by addition. So the natural log of 3x is the natural log of 3 plus the natural log of x. Verify going backwards that if you were asked to simplify natural log of 3 plus the natural log of x into one log, then that would give you the natural log of 3x. Now we can take the derivative. So dy dx is equal to, let's do the easy one first. What is the natural log of x? 1 over x. What's the natural log of 3? What's the derivative of the natural log of 3? Three is a constant. No. 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 Yeah. 3 is a constant. So what's the natural log of 3? The natural log of 3 is a constant. What's the derivative of the natural log of 3?
0.
That is 0. Yeah. So that's the answer. Because the derivative here is equal to 0. Because the natural log of 3 is just, it's 1.0986. That's all it is. It's not a variable. It's not a function. It's constant. Derivative of constants are 0. All right. Questions over that one?
So, natural log of, say the natural log of 4 is still be 0?
The derivative natural log of 4 is 0. Yeah. Yeah. The only time is that you get something that's a function is when you still add x's and stuff. X's or other variables, like this one's going to be a t or whatever. So, all right. Example 6. Find dg dt if g of t is equal to 1 over 5 raised to the t plus 1 power. Again, we have an exponential, we have a base and an exponent, but the exponent is not just the variable t, it's t plus 1. So we can't quite do this one. It doesn't quite follow the rule. It has to follow the pattern exactly. It doesn't quite follow it. So we've got to do some algebra manipulating first. So I'll just tack it on here. This would be 1/5 to the first power times 1/5 to the t power. Splitting up the exponent and making two multipliers here. That is the key. Verify that if you were to resimplify this, you would end up with what you started with. 1/5 to the first power times 1/5 to the t. You would add the exponents. You'd get 1 plus t, which is the same thing as t plus 1. Now, this is just 1/5 times 1/5 to the t. To find dg dt, we're going to take the derivative of this guy. The first part is a constant multiple, so it sticks around, and it's 1/5, times the derivative of 1/5 to the t. So we would use the exponent rule, and that would be 1/5 to the t times the natural log of 1/5. And that's it.
Where's that first one fit come from?
Mhm.
That technically, I don't know, because I guess it's one, two, three, never mind.
Yeah. Yeah, it's a constant multiple, so it just sticks around. Multiply by it at the end. Yeah, it's like if you had 3 times x. 3 times x squared.
So
You don't get rid of the 3.
1/5 plus 1/5 to the t.
No, that's a 0.
Okay.
Yeah, but if it's multiply, yeah, you just carry on. Yeah. All right. Example 7. The amount of bacteria in a colony is given by A is equal to 75 e to the t for time t in hours. How much bacteria was there initially? So initially means that t is equal to 0. So A of t is 75 e to the 0 is 75. Because e to the 0 is 1. How much bacteria will there be in an hour? That's A of 1. So that's 75 e to the first, which is 203.8. I'm just plugging that into the calculator. And then C, at what rate is bacteria growing at 1 hour? So if we want to know the rate, what do we need? We need the derivative. So A prime of t is the derivative of the A function here at the top. So this would be 75. And then what is the derivative of e to the t? That's just e to the t. And so evaluation at 1 hour again results in the same number as before. That's not a coincidence. That's one of the properties of the e function is that you have a curve that is growing at the rate at which it is equal to at that point. So at some point on the e to the x curve, you're going to have some point where that value is equal to 3. The derivative of that, the derivative, the rate of change, the slope of the tangent line, is also equal to 3 at that point. That's the property of e to the x, is that at whatever point you're at, that's the same as the derivative at that point.